Hello everyone, in this video our objectives are to describe what a polyatomic ion is, describe what happens when polyatomic ions bond to other traditional ions or other polyatomic ions, and identify the bonds present when polyatomic ions bond to other traditional ions or other polyatomic ions. So let's first describe what a polyatomic ion is. So here's a definition I put together using the internet and some of my own thoughts. A polyatomic ion, poly meaning many, atomic meaning atoms, and ion meaning a charged particle. So the definition is a group of atoms covalently bonded which together have a charge. It can behave like a cation. Remember, a cation is a positively charged ion if it is a positive polyatomic ion, or it could behave like an anion if it is a negatively charged polyatomic ion. So let's also, before we go too far, take a look at this term right here, covalently bonded. So we also need to think what type of atoms might be involved in the construction of a polyatomic ion. And if we recall, covalently bonded substances or compounds have a nonmetal bonded to a nonmetal, meaning that they are sharing electrons. Now again, they are an ion. So somehow, after they're sharing their electrons, together they're either going to gain an extra electron or lose an electron. Let's take a look at what some of these are. So here we have a list of selected polyatomic ions, and it's located on table E of our reference table. So this is saying a selected few. There are many more, but these are the ones we should focus on. Now, the first sign that you should think of when you see a compound, a formula of a compound, when it's written, if it has more than 2 atoms present, you need to be suspicious that a polyatomic ion is present, and then go inspect this table. So if we have atom X bonded with Y, and you also see a Z, so we have 3 different atoms in a formula. Inspect this table. Now let's inspect it a little bit more deeply ourselves. Let's first take a look at hydronium. Hydronium has a positive charge. Now that is not saying that that positive charge belongs to the oxygen. It is saying that that positive charge belongs to the 3 hydrogens and oxygen when they are together covalently. Let's think of it as they are a team, and collectively they have a positive charge. Now thinking a little bit more deeply, if collectively they have a positive charge, it means that when they joined, they lost 1 electron. Let's go to cyanide. When carbon and nitrogen bond together, they gain an extra electron that is shared evenly between them, so it has a -1 charge. To the right side, we have nitrate. When that 1 nitrogen and 3 oxygens bond covalently together, they acquire an extra electron. Now the interesting thing that we must consider is now that they are acting like an ion, they could bond with either a metal or a nonmetal, depending on their charge. So they could behave like an anion or a cation. So now to our next task. Let's describe what happens when polyatomic ions bond to other traditional ions, meaning cations or anions, or other polyatomic ions. Now to do this, let's play around with some and take a look at what that would look like. Let's hypothetically choose a element that would behave and act like a cation when it ionizes, and an example of that could be potassium or calcium. Let's use both of these. Potassium would like to become a +1. Calcium would like to become a +2. So let me just go ahead and write that down. Potassium would like to become a +1. That's a capital K. And calcium would like to become a 2+. And now let's take a look at the polyatomic ions that are optional to us. Now, if these are positive ions, we would need to find a polyatomic ion that would become negative. And let's go simply for, we say hypochlorite. Now, hypochlorite is grab a pen, ClO2. Now, what would be helpful here is to put brackets around this and the negative sign here so that we know that that negative sign belongs to both the chlorine and the oxygens. Now, what do we do? Well, let's get this out of the way, and let's realize that this looks very similar to an ionic bond now, where we could use our crisscross method to write the final formula, which would be KClO2. But what would it look like if it tried to bond with the calcium, which is a +2? So again, I'm going to write ClO2 negative. Our crisscross would bring the 1 down to here and the 2 down to here, outside of the brackets. And what would that look like? It would look like Ca, keep the brackets, ClO2, but we're going to need 2 of them. Just like in videos past, where this position is the anion, sometimes we needed 2 anions to balance the electrons that were going to be gained by the cation. Here we need 2 of these polyatomic ions to balance the electrons that calcium is willing to give. On the next slide, let's reverse it. So by reversing it, I mean let's create a situation where we have a positive polyatomic ion bonding to a traditional anion. So let's go ahead and look at our possibilities. A positive polyatomic ion, let's pick ammonium. Ammonium is right here, and that's NH4 positive. So NH4 positive. Now again, I like to put the parentheses there so I remember that the positive charge is distributed between those 5 atoms. I'm going to write it twice so that we could create 2 scenarios. Okay, so what can we bond this with? We are going to need a nonmetal because nonmetals will absorb the electrons that ammonium is giving away. And let's pick, let's just say, oxygen. Okay, so first let's do oxygen and see what that looks like. And oxygen becomes a 2-. If we do our crisscross method, the 2 drops down to there while the 1 drops there. And the formula would be written as NH4. But we need 2 of them and 1 oxygen. Let's take another example, and let's say fluorine. Fluorine is -1. If we do our crisscross, we drop the 1 down here, drop the 1 down here, and it would be written in this fashion, NH4F. Now I do not have the parentheses because if I have NH4 already written, it's already implied that there's 1 of them. Next slide, let's take a look at what happens when a positive polyatomic ion bonds with a -1. So once again, this is our list of polyatomic ions, and let's go ahead and grab hydronium and go straight across chromate. And what would that look like if those 2 were to bond? We have hydronium is H3O plus, and the chromate is CrO4 2 minus. Now what would that look like if we did the crisscross, bringing this 2 down, that 1 across, and it would be written as H3O, there are 2 of them, CrO4, and there's only 1 of those, so it balances just nice. So this would be the formula for when hydronium bonded with chromate. Let's pick one other example. Let's just say ammonium with nitrite. Here we would have NH4 with its positive, bonding with NO2 with its negative, and that formula would be written as NH4 NO2. And the reason why it's 1 each is because there's a negative 1 here dropping down to here, positive 1 here dropping down to here. And last, we are going to identify bonds present when polyatomic ions bond to other traditional ions or other polyatomic ions. I put here a series of different formulas that we can inspect. First thing you must know is if I see hydrogen, oxygen, and fluorine, I must be suspicious that a polyatomic ion is present. Similarly, nitrogen, hydrogen, sulfur, magnesium, manganese and oxygen, hydrogen, oxygen, phosphorus, and oxygen. Each of these makes me suspicious that a polyatomic ion is present, and for that let me put our table up so that we can inspect. Once we inspect, we do notice that right here, hydronium, it's right there. And we also have fluorine. Now they both are behaving like an ion, so we do know that an ionic bond must be present, and in fact it's present in this location. But we also know from our definition that a polyatomic ion to begin with is covalently bonded atoms. So right here our hydrogens and oxygens together are sharing electrons. So we have a covalent bond between these two atoms. Okay, similarly, sulfur and ammonium. Ammonium is right here. It is a polyatomic ion, so once again we have covalent bonds holding the polyatomic ion together to begin with. But what is holding that polyatomic ion to the sulfur, which is behaving as an ion? Again, it is an ionic bond and a covalent bond. Similarly, magnesium bonding with MnO4. Where are you? There it is. And the name for that is permanganate. So here we have magnesium ionically bonded to permanganate. In fact, that's its name, magnesium permanganate. Covalent bonds holding these two atoms together, while this polyatomic ion is held to the magnesium with an ionic bond. And lastly, right down on the bottom, we have right here hydronium bonded with this PO4 thing, which is phosphate. Identifying what the bonds are, what's holding the phosphate together to begin with is a covalent bond. What's holding the hydronium together to begin with is a covalent bond. But what's holding these two polyatomic ions together, once again, is an ionic bond. So, before I get off the slide, when you see bonding with polyatomic ions, you will have both ionic and covalent bonds.